Okay, basically, just want to get this semester over with. That's permission. And, I was, why not be honest? And, so for this class, there's not a whole lot left, and it's possible we might be able to wrap up the actual material this week. We'll see how it goes. Now, I would like to know pretty soon how each of you is leaning as far as the final is concerned, doing the oral that's comprehensive or coding option that is on boundary value problems, which is what I'm covering this week. I guess, is there anyone who is leaning toward doing the coding one? Okay, there's one. And from anyone who's online? Okay. You might be the only one. All right. Okay. The reason I'm asking was that I have a space in the schedule for that's meant to discuss the coding one and really take questions. But I figured if it's just one who's doing it, then you can just ask the question that's constant. By Wednesday, probably will have enough information to get going on that. As far as those of you doing the oral, just let me know as far as scheduling is concerned. Preferably either during the last week of classes or possibly, but again, if we're finishing sooner, then. We'll see. Because my other class, I'm hoping we'll wrap up by next Monday. So basically, we just need to find a time slot. We're talking 45 minutes ish. So just let me know of your preference. As long as everything's done by the drop dead date of May 12th, which actually still seems like an eternity away, unfortunately. So, and then that date actually becomes more rigid now because I'm going to be traveling starting on May 13th. So it'll be a lot harder to reach at that point. Okay. More exciting, it's just Ohio, but still. All right. So, okay. So now we'll get to the final type of problem that we'll be considering. We spent a lot of time on initial value problems for ODEs. Now we're going to look at boundary value problems, in particular a 2-point boundary value problem, for which we have a second order ODE. So y double prime is equal to some function f it depends on spatial variable x, and also the solution y itself as well as its first derivative. So this encompasses both linear and nonlinear ODEs. We'll be looking at both. And then because it's a second order ODE, we need two conditions, in this case boundary conditions. So at x equals a, the solution must equal alpha. At x equals b, the solution must equal beta. Okay. Now, some assumptions, just so we don't have any theoretical issues, just so to the leftmost problem. So a function f, as well as its derivatives with respect to y and y prime, need to be continuous on some domain. So x being in the interval AB, and then all y and y prime. This is a rather generous assumption. It's not absolutely necessary, but just simplifies matters. Also, the derivative of f with respect to y needs to be positive on this domain. And the derivative with respect to y prime should at least be bounded. So these are the assumptions under which we'll be working for numerical methods. So there are two methods that I will cover. There's more methods. Now this is drawn from chapter 13 in the text. Chapter 13 actually has 4 sections covering 4 different methods, but I'm just going to cover 2. And the first is the shooting method. That'll be the subject of today. And then I'll get to the other one, finite difference methods, on Wednesday. So that's what the shooting method is. We get to fall back on everything we've just been doing with initial value problems. So we transform the boundary value problem into an initial value problem. So the ODE is the same. And then we have this boundary condition, which is now thought of as an initial condition. But because it's a second order ODE, you need to have 2 initial conditions, one for y and one for y prime. So y prime of a at the left endpoint is equal to some unknown value t. So that's for rough. We need to find the right value of t so that the solution that starts at y equal alpha at the left endpoint x equals a needs to hit the target. That it starts at this point, we need to travel from x equals a to x equals b. And once we get to x equals b, we need to hit y equal to beta. That's why it's called a shooting method. We want to try to find the right trajectory, the right slope at x equals a so that we'll hit the target at x equals b. So to leverage everything we know about solving initial value problems, like the time-stepping methods we dealt with, we'll rewrite second order ODE as a first order system. Now here's something to keep in mind. The 1 and the 2 here, those are superscripts, they are not exponents. I am not squaring a dang thing all day long. So just don't. In retrospect, I probably should have put the superscripts in parentheses. I have done that on other occasions. Not sure why I did this time, I think just fatigue, writing fatigue. So again, I'm pretty sure there's nothing in here that's squared. Okay. Someone's going to think that anyway, I just know it. Okay. All right. So I defined 2 variables. Y1 is y, y2 is y prime. So now I have a system of ODEs in first order ODEs in y1 and y2. So y1 prime is just y2 based on a relationship between y1 and y2 here. How are defined. And then y2 prime is the same as y prime prime, or y double prime, and that's equal to f. But now f is described as a function of x, y1, and y2 instead of y and y prime. So here we have a... Okay. It happened last class. Doesn't get any less startling.
Oh my gosh.
Okay.
Is it the draft? I mean,
Yeah, I'm Windows being open.
Okay.
Yeah. Yeah, it's pretty powerful.
This building's weird today.
Okay. All right, gotta recover from that. And then here are the initial conditions. So y1 at x at the initial time, if you will, at a, y1 is equal to alpha. That's the first given boundary condition. And then y2 of a will be this unknown trajectory. So the idea is we want to find the right trajectory, which I'll call t star, the right slope, so that this equation, which gives me the value of the solution y1 at x equals b, must equal beta. So you can think of the shooting method as finding a root of this equation. All right, now there's 2 categories of problems linear, nonlinear. The linear is far easier. That's why I'm going to consider it separately. Okay. So when we have a linear boundary value problem, we can write the ODE in this form, because we have some coefficient times y prime plus some coefficient times y plus some other function of x. So now we know what df/dy is, and we know what df/dy prime is, just from the coefficients that we see here. And that means that the coefficient q of x must be positive, based on the assumptions that were made at the beginning to ensure a well-posed problem. So here's what we can do. We can take advantage of the linearity of this ODE. So first, we just go ahead and solve this problem, where we have the original boundary condition at the left endpoint, and then we'll just assume that the slope is 0. And then we solve this problem without the r of x that's left out of the ODE, where now the value of a solution at the left is 0, and we have a slope of 1. Because now, if I define y to be a linear combination of these solutions, then here's what I have. That this linear combination of y1 and y2 will satisfy the ODE. So that part's taken care of, just by linearity. And now let's see what happens at the boundary. So at x equals a, we have y1 of a, which is the solution of this problem, so it must equal alpha at that point, plus t times the value of y2 at a, but that was prescribed to be 0. So this linear combination of y1 and y2 satisfies this boundary condition at the left endpoint. And then the derivative at the left endpoint will be equal to the same linear combination of derivatives, but the first solution, y1, is equal to 0. But the derivative is equal to 0 at x equals a. And then this is equal to 1, so the slope is going to be t. And now we can figure out what the value of at the right hand point is. It's whatever this solution is plus t times whatever this solution is. So now what we can do is we can set this equal to beta. And because these values, y1 of b and y2 of b, are now known once we have solved these problems, we just have a trivial equation to solve for. Because the ODE and the boundary conditions are linear, the equation that we're trying to solve for t is also linear. So we just go ahead and solve it. So the only numerical part of this is whatever you do to solve these equations. After that, it can really be done analytically from there. Any questions about this approach to finding the right trajectory? The only reason I didn't write out the formula for t was I think I made it a homework problem. But it does require that this value, y2 of b, has to be non-zero. Although one of the homework problems, I don't recall if I assigned it from this section, is to actually prove that under the assumptions that we have, this will all, we can guarantee this, that this value will be non-zero. So as an example, here's our linear ODE. So in this case, the coefficient p is 2, Q is -1, and then wait a minute. Let's do the ill-pills problem. I think I did. Yeah, Q would be -1, and then this is our R of X. And this problem can still be solved. Okay. A unique solution is guaranteed if derivative of f with respect to, oh, wait. Okay, yeah, if a derivative with respect to y is positive, yeah, that's what we want, to ensure this guarantees a unique solution. It's sufficient but not necessary. Certainly, this is a problem that can be solved analytically. Okay, so here's our original boundary value problem right here with these two boundary conditions. So now I solve this problem, same ODE, same first boundary condition, and I set y prime equal to 1. And that's something you can solve using techniques from like our first ODE class, like Map 285, which actually exactly one of you in this room would have taken. So I guess throwing out course numbers doesn't really help very much. But your first ODE class, you can solve this. Then you solve this ODE where this function is stripped out. This boundary condition is I think we have. I think I have a mistake here. Yes, I do. This should be 0 for the first problem. Yeah. And then for the second problem, the derivative should be 1. And yes, I really am checking to see if I made that same mistake in the book, because dang it. Oh, it's correct in the book. Okay. Whew. All right. And then that's the solution. So now, the solution to my overall problem is the first solution y1 plus an unknown value t times the second solution. Now I'm not working on a domain x going from 0 to 2. So what I have here is I plug in x equal 2 into my two solutions, into y1 and into y2, and I get this equation. So this is the value of my solution at the right endpoint, x equals 2, in terms of the unknown slope, t, and I set this equal to the value that I want at x equals 2, which is -4 for my original boundary condition. Now I have this algebraic equation, which it's a linear equation, so I can just solve that for t, and t equals -2/3 happens to be the value that works. The question is about how this example unfolds. So in fact, in this case, because these two ODEs can be solved analytically, you're not really using a numerical method at all, not for this problem. But that changes once we move to a nonlinear problem. now let's look at the nonlinear case. Now, here is the same system of two first-order ODEs that the original boundary value problem is described as, the original ODE is. And this is the same equation that we dealt with before, but had to be satisfied, that once you solve this system of ODEs, and you plug in x equals b to get the value of the right endpoint, you want that to be equal to beta. So we're still trying to find a root of this function. Now, the case of a linear ODE, the problem of finding t can still be described that way. It's just that this function turns out to be a linear function. So there's nothing to do, there's very little to do really. If an ODE is nonlinear, then this becomes a nonlinear function of t. Therefore, we need to use some root finding method, so for example, some kind of iterative method to find a value of t that will work, that will make our solution satisfy the right endpoint boundary condition. So we can use bisection, fixed point, secant, Newton's method. In this case, I'm going to talk about using Newton's method due to the rapid convergence. Now, so if I'm going to solve this equation, f of t equals 0, using Newton's method, of course with Newton's method you need the derivative of a function you're trying to find a root of. Keep in mind it's a function of t, even though y1 depends on x also. So, I'm going to define z1 to be the derivative of y1 with respect to t. And then the derivative of f will be this derivative with respect to t, but plugging in x equals b. Now keep in mind, y1 is a function of both x and t, because you're solving a boundary value problem, an ODE that depends on, whose independent variable is x, but then you have t as a parameter, so a second variable. So what follows here, keep in mind, all these y's and z's, they are functions of both x and t, can have derivatives with respect to both x and t. So to help keep the notation straight, wherever you see a prime in here, that's a derivative with respect to x. Wherever I need to refer to a derivative with respect to t, I'll use a subscript here. But also keep in mind we can differentiate in whatever order we need to. We can change the order of differentiation if we need to. So we need formulas. We need a formula for derivatives of z1 to be able to carry out Newton's method. Okay. So I'll define z1 to be derivative of y1 with respect to t. And then z2 will be the derivative of y2, which is also y prime with respect to t. So, since I have ODEs that define y1 and y2, I can obtain from that ODEs that will describe z1 and z2. So, while I'm solving these, I can also solve these. So how do I go about getting ODEs for z1 and z2? Well, z1 prime, if you keep in mind that z1 is dy dt, so this expression right here is a derivative of y, first with respect to t, and then with respect to x. But then if I take the derivative of y with respect to x first, that's y prime, which is also y2. So really what I have here is also the derivative of y2 with respect to t, but that's z2. So that's how I wind up with z2 here, by reconsidering the order of differentiation. Another way of looking at it is if I just take a derivative of both sides of this with respect to t, derivative of y2 with respect to t is defined to be z2. I guess in retrospect that's a little easier. And then here, if I take a derivative with respect to differentiation with respect to t and move it inside the prime, I would get z1 from y1. Then I move to the second ODE. And if I take a derivative of if I take a derivative of both sides of this ODE with respect to t, so on the right side, by chain rule, I'll have df dy derivative of y1 with respect to t, but that's z1, plus derivative of this with respect to y2, or y prime rather, and then I'll multiply by y2 with respect to t, but that's z2. So that explains the right side. And then here, again, I move the differentiation with respect to t inside the prime, and that gives me a z2 where formerly it had a y2. So now, to carry out Newton's method, I really have a system of 4 ODEs. There are 4 unknowns, y1, y2, z1, z2. So I go ahead and solve those by whatever time-stepping method I choose. And once I get from, of course, really it's stepping through space. I'm stepping from x equals a to x equals b. But I'm thinking it kind of like using a time-stepping method to do it. So once I reach x equals b, I guess I can call it space stepping if I want. Once I reach x equals b, I will have all the information I need to carry out an iteration of Newton's method. And here are my initial conditions. Here are from the original problem. This comes from the original boundary condition at x equals a. And here I have my unknown trajectory t, for which I need an initial guess to carry out Newton's method. So whatever I have here will be my current guess for Newton's method. So now I take the derivatives of these equations, both sides, with respect to t. So derivative of this with respect to t will be z1. Alpha is a constant, so I get 0 here. And then here I'm taking derivative of t with respect to t, which is why I have 1 here. So these are the 4 initial conditions for my 4 ODEs. So now what I can do is show you the overall algorithm. If I use Euler's method, so forward Euler for time stepping, or space stepping, wrapped within Newton's method to find the correct value of t. So the algorithm, okay, I need to switch to Adobe Reader, so. All right. Okay. So here's the algorithm. I'll make it a little bigger. Seems to be a delay when I do this. Okay. So this is the shooting method, using Newton's method for the iteration, find t, and using forward Euler to solve the ODEs involved. So at the outermost steps, it's really Newton's method. We need an initial guess. Actually, one of the homework problems discusses how to get some guidance towards choosing the initial guess. And then here we define h. Now h in the last chapter was used to refer to a time step. We're going to use h in the same way this time, and even though we have a spatial domain x going from a to b, but h is how we're going to step from a to b. So we're dividing the interval AB into n plus 1 subintervals. And the reason for that is that then our solution will have n points. So we're defining n interior grid points because we know what the solution is in the boundary. That's what, because of our boundary conditions. What we're solving for consists of a value of y in the interior of a domain AB. So we pick n equally spaced points in the interior of AB, and this will be the spacing between them. So, you have it on your own. This is the spacing between them. Okay. Now, this outer loop is for Newton's method. So, everything inside this outer loop, all this, is meant to carry out one iteration of Newton's method. It's just going to take a lot of work. So I'm using k to count my Newton iterations. So inside the loop, what do I need to do? I need to solve my 4 ODEs, my system. And whatever guess I have for my slope, that plays a role in one of the initial conditions. And that's what we see here. That my current Newton's method guess, so initially t0, is my initial value. And then the other initial values are always the same regardless of Newton's method. So now I set my initial values. This inner loop carries out the time stepping. So I move to my next point at x, and starting from x equals a and taking steps of width h. And then here is Euler's method. New value is equal to previous value plus your step size times your time derivative. So whatever's multiplying h, those are the time derivatives. Okay, derivatives with respect to x in this case. I know it's confusing. From your ODEs. So if you were to look at the ODEs, for y and for z, what you have on the right side, so for all your derivatives, is exactly what you have here, multiplying h. So then you carry out all these steps, and by the time, and here, notice I going from 0 to n. So once you completed all n plus 1 steps, you're stepping past the n interior points, and then one more step to get to the right boundary point. So that's where you're at. That's where x is. Okay. By the time you get here. So now, this is your Newton's method step. Remember formula for Newton's method. New value equals previous value minus the function value. And all you're doing is you want the value of the solution at the rightmost endpoint to equal beta divided by the derivative. But the derivative of this with respect to t is just this part, because beta is a constant. So really you want the derivative of just that in respect to t. You're dividing by that. That's your Newton's method. And now Newton's method will keep going. It's just that one evaluation of your functions, your f and f prime from generic Newton's method, requires doing all this work. Now, you might want to use a different time-stepping method, possibly, like for instance, whether it's 4-4 Runge-Kutta, or maybe even something in between, like explicit trapezoidal method, so that maybe you can get away with less computation in here. And here we're using a rapidly convergent root finding method. Or maybe you don't want to use Newton's method. You could try using a secant method. So then they would tell me why switching to secant method would be a whole lot less work than what you see here. Like what steps would be cut out? What's it you don't need from doing secant method as opposed to Newton's method?
Your old iterate, that's your function over your derivative. I mean,
Alright, think about the difference, what changes in Newton's method to get secant method? What's the difference between them? Yeah, you don't have to evaluate a derivative at all, because you're just using a difference quotient. So, you don't need z at all, it's gone. So now you're solving only a system of 2 ODEs rather than 4.
Oh, yeah, no, yeah. Okay.
And what you would have in its place is, in the denominator, you would have a difference of y values. So you have, there's a bit more of a storage requirement, because you have the y values you just computed, and then from a previous iteration, you don't need to store all the y values. Really what you need is one at the right endpoint, x equals b. So actually the storage difference is minimal. And in the numerator, you have an extra factor of a difference of t values. And that's it. So, I mean, secant method is already known to be less work per iteration than Newton's method, just because you don't have to evaluate at prime. In this case, that makes a particularly big difference. You're cutting out all this. Now, that iteration, you might take slightly more iterations, but the difference is considered slight enough that a lot of people prefer secant in a situation like this. All right. What you can always do if you were to find the value of t such that if you use that as a slope and you find that your solution value is less than beta, and then you try a different t and you find that its solution value at x equals b is greater than beta, then you can use bisection. Because you have your function capital F, you can see where it has a positive value and a negative value, so you keep doing bisection. But each iteration of bisection would still be solving at least these 2 ODEs. So, and bisection takes a lot more iterations, so that could be a lot more work. And so the thing is, as far as coding this up, the Newton's method part requires hardly any code at all. It's like the actual Newton step. It's all stuff here where the main work is done. For a coding option, the final requires 2 versions of the secant method, so not 2 versions of a shooting method. So an implementation of what you see here, and then a modification of it that uses secant method instead of Newton's method. Like if basically you do Newton's method, then you start tossing stuff out. Okay. So, here I have an example. So here we have a nonlinear boundary value problem. So this right-hand side is a nonlinear function of y and y prime. On the domain x goes from 1 to 2, these boundary conditions. It happens to be possible to obtain an exact solution, but that only happens in special cases. Okay. So then I have here a MATLAB code snippet. I did not supply this function because that's one of the problems. But for a coding option, I have code like this that is designed to set up a test problem. So then you can just run test code and it'll compute the solution using your code and then plot that computed solution, also plot the exact solution. You can check if they match, and then if they do, then you know you got it right. So this is just meant to carry out that comparison. and handle the graphing part. So in this case, there's a slight discrepancy between the approximate and exact solution, but considering that it's just using the first order method to solve the ODEs, the Euler's method, not exactly a small time step, that agreement's pretty good. Okay. Oh, yeah, here's a suggestion about, or problem asking about, what would be a nice generic way to choose the initial guess from a slope. Now, if you're doing CCAT method, then you need 2 initial guesses. All right, so questions about the shooting method?
No, but I like what you wanted to name the file in there. Shoot you, just round
If you ever approach it, I'll show you on Wednesday, finite difference method. I think actually that's more efficient than this, but it's very common. Like you already have, if you think of your problem as similar to another problem you already know how to solve, then it makes sense to try to take advantage of that. Whether that's the best option is another matter, but you know, it works in this case. Alright. Now, so any questions about, well, anything, including homework? Has anyone been doing any homework? Oh, just a little bit, but yeah. I guess we could fully catch up on grading soon. All right, I guess we'll wrap this up on Wednesday then.